Avogadro's number mole ratio. Let's look at these two questions to practice those concepts a little bit more. How many molecules are in 1.75 moles of carbon dioxide? So you're not being asked about a different substance. You're being asked only about the same substance. And you want to go from moles to molecules. Whenever there's moles involved and ions, particles, molecules, atoms, etc., you use Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd items, things, over 1 mole. And you can define those items to whatever you're looking for. So in this problem here, we're given 1.75 moles CO2. And we want molecules, CO2. And the only way that we can go from moles to molecules is to use Avogadro's number. So we define that in terms of our units. So we know 6.022 times 10 to the 23rd molecules over 1 mole. Then we just apply that. So if I start with 1.75 moles CO2 and I want molecules, the molecules is going to go on the top. And the moles is going to go on the bottom. Then moles will cancel, and plugging that into your calculator, you will get 1.05 times 10 to the 24 molecules carbon dioxide. Now, you want to check sig figs. You have 3 sig figs for 1.75, 3 sig figs for 1.05. You have your unit and your compound. Now, if you were asked to go to moles instead of molecules, you would simply flip your conversion factor, knowing that the ratio from moles and Avogadro's number, that items, molecules, atoms, etc., that's your conversion factor. You use it always writing what you want over what you're trying to get rid of. Let's look at the next problem, putting a little bit more of mole ratio into the concept. Propyl acetate, which is C5H10O2, gives the odor and taste to pears. How many moles of carbon are present in 1.50 moles of propyl acetate? So given here, 1.50 moles of C5H10O2. We want mole carbon. Okay, so we're not looking for molecules, grams, or anything like that. We're just looking for carbon, moles of carbon. So the same unit, but different compound. So whenever you're looking at a different element or different compound from what you're starting with, you use a mole ratio always. So you look for the ratio of the substance to what you're given. I like to do this by writing out how much I have of each in my compound. So I have C5H10O2. And if I write myself a little decomposition reaction, I have carbon plus hydrogen plus oxygen that make up this compound. I have 5 carbon, 10 hydrogens, 2 oxygens. 5, 5, 10, 10, 2, and 2. So I'm balanced. All right, so I'm looking at carbon and propyl acetate. So for 1 mole of propyl acetate, I have 5 moles carbon. The coefficient is my quantity of each compound element. So I have a 1 to 5 ratio. Now you use that to convert from one to the other, knowing you can always and only use mole ratio, so the coefficients from the balanced reaction, to convert from one substance to a whole other substance. It cannot be done in any other unit. This is because your chemical equation tells you the relationship they have in quantities of one another according to the law of mass. All right, so we have 1.50 moles of propyl acetate. And since I want carbon, and I have to use my ratio, I'm going to place 5 moles of carbon on the top, 1 mole of C5H10O2 on the bottom. Now, I can see that my moles of propyl acetate cancel out, and I'm left with my moles of carbon. If I plug that in, I get 7.50 moles carbon. I have my 3 significant figures, my unit, and my compound. So key is always to make sure that you have a balanced chemical equation, that you determine the ratio between what you're given and what you want, and that you always use the mole ratio, the coefficients from the equation, to convert from one compound to another.